I am Harsha Komaragiri and I will be presenting the working mechanism of my project called Smart Sunroof, which runs using the Arduino Uno R3. And as part of my coursework in 561, I was required to do a prototype with an idea which has scope to be developed with some of the future emerging technologies. I'd like to say that my internship experience in my senior year during undergrad helped me come up with the present prototype concept. I interned at a solar power plant in which there were several solar modules or panels, as we call them, and they required automatic cleaning as they percolated a lot of dust, and a cleaning bot was necessary, and manually cleaning them would have been a laborious task, and it simply made no practical sense. But this bot, once it was introduced, it was basically operated using a Zigbee module, which is a very efficient wireless technique. And this was controlled from the control station of the power plant, and it made the maintenance and operations very easy. The working model in this project was designed to carefully monitor weather conditions such as frequent rains and heavy winds in horticulture farms. The model it makes use of a linear actuator which has static load, and it encloses a panel over the plants moving along a wheel track. The microcontroller chosen for this project is an Arduino Uno, simply due to its simple configuration. I've chosen the Uno as this prototype requires just two sensors, and it's also cost effective. We also have a basic raindrop sensing module and wind sensor, and both of them give out analog output values. Unlike the traditional anemometer, which runs on a propeller-driven generator, basically a fan, the wind sensor used here has higher sensitivity and it responds at any instant of time bit like. The motor driver used is the L298N, as we need to run just one stepper motor, and it's operable up to 35 volts. And since we're using 12 volts DC supply to the motor, this is going to suffice. It also has a good heat sink. Again, we really don't need much of heat protection, but it's still a safety precaution. As for the panel I've used, it's a plexi sheet. It has high durability and it's light in weight. It's fixed to a wheel that is confined to move back and forth along a track. On the Arduino board, we connect the corresponding supply pin, analog input-output pins, and we complete the circuit by connecting the ground on the breadboard. The water module and the sensor controller are separated by a positive and negative terminal wires as shown in the diagram. The wind sensor is interfaced using four of its soldered pins. First, the raw loop voltage pin, also known as the RV pin, and the thermistor pin called TMP. They connect to the two analog pins on the Arduino. Supply and ground connections remain the same as before, similar to the water sensor. And in here I've calibrated the wind sensor to increase its sensitivity to record data from 15 miles per hour and above. The motor driver consists of supply terminal pins which connect to a 12 volt lead acid battery. The four output pins connect to each of the pair of coil connections of the stepper motor. Normally, a protective shield for the Arduino been would be required if the supply had been more than 12 volts. But since our operating conditions are minimal, I haven't used one. Bipolar steppers they basically consist of a pair of coils, and the stator of each of these coils they get magnetized through a DC supply. So the poles of each of these coils keep shuffling consequently, and this causes the magnet to move in the corresponding direction. The permanent magnet rotor, as located at the center seen from the slide. This rotates in continuous steps to perform rotation, provide smooth operation unlike the other motors. As can be seen from the front view, a typical NEMA 17 stepper motor is a square plate. It has a square plate measuring 4.2 centimeters square as a cross-sectional area, and it has a shaft at the center that measures about half a centimeter in diameter. And in this project, the motor comes coupled with a lead screw, which is coupled onto the shaft, and that acts as a rotor. The lead screw used here is of Acme threading profile, which is also known as trapezoidal threading. Here the angle of each thread circumference is about 29 degrees, and the reason is simply because generally this thread in design called Acme design is known for high strength and loading capacity, and I've used this particular threaded rod for the purpose of carrying heavy loads, which makes the rod move with higher torque. The operation mechanism in this model is that of an actuator. Actuators have applications everywhere that involves moving a load along a specific direction. Also, in using a stepper motor for this purpose, it serves good accurate movements due to its stepping function. Another benefit of using this motor is that it draws constant current and has a constant holding torque. So since we've only used a static load in this prototype, the power drawn from the supply doesn't vary much and gives consistent performance over prolonged periods of time. While interfacing and we're writing the program for interfacing the water sensor, we have the lower and upper limits of the maximum permissible integer values that the module reads in dry condition. These are 1024 for dry and 0 for wet conditions when it's completely immersed in water. The loop reads the void loop. It reads the analog input at port A0 and prints the warning in case the module gets wet. In my prototype, it is coded to print out after an integer value goes less than 500, and it begins to activate the motor driver in parallel with the wind sensor. For coding the wind sensor, we have the raw loop voltage, which is RV, and temperature output connected to analog pins 1 and 2. Other initializations include the wind speed units recorded in miles per hour and their corresponding voltage values. During void setup, the input ports detect the analog input from both the sensors and activate the stepper motor. To code the stepper motor, we need to include a stepper motor library called stepper.h, which includes various functions such as step.begin and .digital write for running stepper motors. We declare our steps per revolution, which is 200 for the NEMA 17 motor from calculating using the stepper angle equation. The 4 pins 8, 9, 10, and 11 give a digital output of 3.3 volts to the stepper motor driver. And this runs the motor at a speed of 80 rotations per minute. Basically, higher RPM leads to higher torque of the motor, and 80 RPM was found to be sufficient for this particular load. Now looking at the design flow, we have two of the sensors which give out analog input simultaneously to the Arduino. The Arduino then runs the code as what we've given in the IDE, and this spits out the digital values from the 4 pins to the motor driver. The motor driver then runs this through the pair of wires which it connects to the stepper motor, and these wires are color coded as red and blue for coil 1 and green and black for coil 2. Now coming to the result, we have uploaded the code to Arduino, and it immediately starts reading the status of our code on the serial monitor with a delay of 1 second for each data, and this prints out data continuously when the motor runs the threaded rod. The value read here is 338, which implies that the module was just above the threshold of being wet. Well, future prospects for this model include integrating artificial intelligence, wireless technologies such as Zigbee and 5G modules to be remotely monitored from any geographical location, IoT, and we have cognitive applications, which include predicting weather patterns using computer vision for such systems. So they activate the uh, robotic arms in a greenhouse or horticultural farm. Another example is employing SCADA to allow massive scalability of such operations as they would conventionally require a lot of manpower, but in this case, they're going to be replaced by smart machines. And I hope this prototype has given a brief insight on the positive prospects, possible robotic applications that it can provide in the near future in the horticulture industry. Thank you.